Often, when working with three-dimensional medical volumes, you might want to change the size of your scan as it might be too large for the system. However, resizing a volume is not as trivial as resizing an image because we also need to change the voxel size. In the subsequent cells, we will take a look at how to resample a volume to a smaller size. At first, we should remind ourselves of the current shape and pixel size of our brain MRI scan. Alright, let's resize the brain MRI from 256 by 256 by 150 to 128 times 128 times 100. To do so, you can use the confirm function, which accepts a nifty file as its input, followed by the desired shape and the voxel size. Last but not least, you can pass an orientation string indicating the orientation of the resulting resized volume. Of course, we have to change the voxel size as it would be otherwise impossible to reduce the shape. Let's simply go with a voxel size of 2 times 2 times 2 millimeters. Alright, at first we import nebabel.processing, then we define the voxel size variable, which takes the triple corresponding of the new voxel size. In our case, simply 2, 2, 2. Then we can directly define the variable brain MRI resized, which takes the result of nebabel.processing.confirm. We use the original brain MRI as the input, 128 times 128 times 100 as the new desired shape. Next, we pass the voxel size the new volume should have, and last but not least, our desired orientation. We simply use PSR, which corresponds to the original orientation of our brain MRI. Let us directly define the brain MRI resized data variable, which stores the result of the get_fdata function. Let us take a look at the shape of the new volume and also the new pixel sizes. Perfect! The resized volume has our desired shape and also our desired pixel size. Cool! Let's now use a subplot to visualize a slice of the original brain MRI and the slice with the same index of the resized volume. To do so, we create a plt.subplots figure with 1 row and 2 columns. Then access the first axis object where we pass the 50th slice of our original brain MRI data. Of course, this time we don't forget to add the color map. Let's quickly copy this line and replace brain MRI data with brain MRI resized data. Of course, we also change the index of the axis object. Both images show roughly the same content and have the same orientation. Of course, the original image has a much better resolution than the resized one. Due to the enlarged voxel size, the right plot visualizes a different location in the head. The last section of this lesson will demonstrate the application of normalization and standardization using both a CT and an MRI scan. Both the CT and MRI scan are distributed by the Medical Segmentation Decathlon Challenge and as usual already provided in the corresponding directory. You can find the link to the dataset, the relevant publication and the license in the Jupyter Notebook. SCT scans have a fixed and absolute scale from -1000, which corresponds to air, and 1000, which corresponds to water. You typically don't want to perform normalization to keep those scales. In practice, you can assume that all values within a CT scan lie between -1024 and 3071. You can therefore standardize the data by scaling the volume with the constant 1 divided by 3071. At first, we use nebabel.load to load the lung CT and store the corresponding volume in a variable called lung CT data. Next, we perform the standardization step. To do so, we simply divide our lung CT data variable by 3071 and store this result in a variable lung CT data standardized. We can quickly define a figure and use the imshow function followed by the numpy.rod90 function to visualize a single slice of our standardized volume. The rod90 function simply rotates the image by 90 degrees to make sure that it looks alright. As you can see, the standardized image still absolutely looks like a normal CT because all scales were kept. To demonstrate how to perform windowing, let's define a variable called lung CT lung window and then use the numpy.clip function, which gets an array as its first argument, then a lower bound and an upper bound. As an example, to get a nice lung window, we can clip all values smaller than -1000 and larger than -500. Next, we can simply reuse the code from above to visualize the same slice but with an applied lung window. As you can see, this yields a great visualization of the lung and the corresponding vessels, but destroys all information within the heart or the muscles around the thorax. Additionally, we can define another variable called lung CT soft tissue window, where we again use the clip function, pass our lung CT data and clip all values outside the interval defined by -250 and 250. We use the plot from above to visualize the slice with applied soft tissue window. As you can see, the lungs are nearly fully black, but you have lots of information within the heart or the muscles. This is especially true when inspecting a slice from the abdomen by changing our slice index from 50 to 5. As you can see, you have a beautiful visualization of all organs and muscles within this region. Last but not least, it's time to take a look at how to normalize and standardize an MRI scan. At first, we define a variable called cardiac MRI, which stores the nifty file containing the cardiac MRI scan. The file name is la_083.ni.gc. Additionally, we directly define cardiac MRI data, which stores the corresponding volume. When working with MRI scans, it is often helpful to perform set normalization. To do so, we at first compute the mean and standard deviation of each individual subject by simply defining a mean and standard deviation variable and use numpy.mean as well as numpy.std on the cardiac MRI data. Based on this mean and standard deviation, we can now compute cardiac MRI normalized by at first subtracting the mean from our cardiac MRI data, followed by division by the standard deviation. This normalization technique is called set normalization. Based on this normalized cardiac MRI scan, we can compute the standardized cardiac MRI scan. One example of standardization is called min-max scaling, where we at first subtract the minimal value of our normalized cardiac MRI scan from the complete volume. and then divide the resulting array by the difference between the maximal value in the normalized cardiac MRI scan and the minimal value within it. To verify that our min-max scaling worked as expected, we can print the minimal and maximal values within our standardized MRI scan. If those values are 0 and 1 respectively, everything went as expected. Additionally, we can take a look at the mean simply out of interest. Awesome! The minimal value returned by numpy.min is 0 and the maximal value is 1. Perfect! The last code cell we execute before diving into our first real medical problem has to visualize a single slice of our standardized MRI scan. We simply define a figure one more time and use the mshow function on a single slice. Here you can see a sagittal view through the heart. Wow, this was a really tough but extremely important lecture. Congratulations for powering through it. Now you know everything you need to know to tackle problems that deal with medical imaging data. You know all the pitfalls, as an example, how different orientations within a training dataset can ruin your training, and also how to check for that. In addition, you can also handle volumes of all sizes and shapes. If not already done, I highly recommend to take a look at the provided Jupyter notebook, because it contains some more detailed explanations and also an excursion about the reorientation of three-dimensional volumes. In the next lecture series, we will combine everything we have learned so far with a convolutional neural network to detect pneumonia in X-ray images. Alright, now we're really getting started. Have fun and happy learning. Thanks.